Hi, good morning, doctor. My name is Shangela, or you can call me Jared. And this project I'm presenting today is the double edge decompiler large language models in malware reverse engineering arm race. So the direction of this argument is relatively simple. It's try to understand the trend of how malwares are doing today. What's the trend of malware analysis going with LLMs in the mix? LLMs are being sold to us as a breakthrough capability, and really, malware analysis, reverse engineering is just a fancy way of saying taking the malware apart and understand what it does. With the mix of LLMs, they are genuinely useful, but this very same capability that we have for the defenders is also available for the attackers, which is the dual edge compiler thing that I'm trying to present, right? So the the other thing that I would like to call out is the defensive research has a much longer and harder road ahead as you look through the research and throughout the flashy numbers, and I will show you why. So, here's the summary of the whole argument. You have one LM model, which what matters to us is the ability to comprehend text or understand code, and then you span out into two edges. You span out to the defensive edge, and you span out in the offensive edge. What I'm trying to share in this one capability on this one slide is necessarily it doesn't necessarily from one end have people that are trying to defend. You have, on the other hand, people that are trying to do offense. And looking at this, people in both sides, they are trying to race with between each other to see who's faster. And in one end, if one the defense have improvements, the other has another improvement. So it's like an arms race that the cybersecurity space has in unprecedented speed has faced are facing right now. So why do we even want this, right? Two two examples. One is the scale. The second is obfuscation. So basically, by obfuscation, I mean malware authors are deliberately transforming their code to make it a little bit harder to read. And Scanco has a research that basically calls this out as we talk about these two particular bottleneck the malware analysis analysts are facing. Putting these all together, the manual bottleneck obfuscation means a very great deal of malware that is never fully analyzed, and the defenders ended up reacting to threats they do not understand, and the gap that's the gap that we hope in the industry hopes LM could fix. And when you look at why LM fixed this problem is old machine learning models needs a very specific structure. And it only works well with specific structures like signatures. And it doesn't really work well with text-like materials. But looking at reverse engineering, what it does is deassemblies, decompiles pseudocodes, which are exactly the kind of text LLMs are trying to do, right? And of course the engineers can read everything through it, but with the help of LLM, it's really helpful, and it's used to actually act as an assistant to really read and summarize and explain the point that really matters instead of the engineers scrambling for the manual tasks they are doing. And really, when I talk about the next three slides is going to talk about three capabilities on the defensive side. One, it's the obfuscation. So Patsakis and his colleagues used GPT-4 to recover nearly 89% of the domains hidden inside obfuscated emotet scripts. Generally useful results, but looking closer into the numbers, something that you don't see is like it's only looking at one single malware family. It's impressive, but it's relatively narrow. And within the same exact research, they actually use different models. The weaker models actually invented plausible looking URLs that simply never existed, which is one of the bigger problems that we face in the whole, the idea of it, and the whole defensive side. And the third result is in Navy. It's the one that I want you to remember. In a separate framework studied by Scanco and colleagues, every single one of the 7 to 8 commercial models tested failed against combined obfuscation. Not some, all of them. That is very hard ceiling on the current capability. So deobfuscation is a real simple case, and it collapses. The obfuscation, it basically collapses as the obfuscation gets more sophisticated. And the second capability is really about behavior summarization, turning raw data into plain language descriptions of what the malware does. um, this attacks directly attacks the engineers cognitive load, because sometimes in most cases, the engineers are not relatively experts yet, and a lot of times when you look at this, the behavior summarization also helps engineers to really save a lot of time. And we have two researchers here. When you look at the whole two researchers, Malware took 133 malware samples, and fitting again, it works, and it provides a quite high accuracy in terms of explaining what it does. But as you can see, it's very tiny against the real world scale. And Malpairs, on the other hand, by Walton, use 200 Android packages to really look at whether or not the classification rate is high, and it reaches a 77% accuracy. But they have also called out this is not good enough, and this is not good enough for the whole for what you might call it, commercial ready product. And next is the detection. It moves from describing the malware to making decisions about it. Is this malicious? Whether which exploits which weaknesses does it exploit? This is the most eye-catching number, and granted, I really want to call this out as well. This is the research that used the most amount of archives, so basically data sets. 4,000, nearly 4,000 in particular, 3,839 as you can see. And it's able to detect whether or not they are malware in 97% accuracy. So this is a very impressive number. But again, when you look into further associating the malware to the right CVE, or asking that question even further, the hard reasoning task collapses. And again, back to the point, the whole approach is quite monotone. It's only one family. And really, I wanted to tie this whole argument to kind of ground it back to how it's wired in practice. You have the binary, you have the decompiler, which turns the binary into pseudocode. And this is where, and then connect it to an MCP layer, or a model context protocol layer, to call tools like Ghidra MCP, and then wired it directly to LLM to kind of, reason over the code and provide a summary into the for the engineers. And really, this is the usual framework that everyone uses in order to, ground it back to how it's working. But three limitations stuck on the whole pipeline. One is the context window, second is the cost, and the third, the worst part, the hallucinated logic. Creating things out of nothing is the problem. Let me summarize this as the whole thing for the defense side with five numbers, as you can see here. Looking at the numbers together, it it looks like a triumph, right? It looks amazing. Reading every single result that you can see here, 89%, 97%, 77%, 133. The numbers look amazing, but looking closer, everyone has a caveat, right? Reading together, everyone has like a narrow data set, a single language, one single campaign, and it works worse with the results with harder tasks, like associating the malware to say whether or not which CVE actually is being used in this particular use case, which is the most important capability that we want to draw out using LLMs. And now the turn. Everything so far has treated malware, the assistant or defender, treated the model or LLMs as defender assistant. But on the other side, one capability or one research for a kill, LM Malworth, used only 10 Windows sample, With LMs, they literally created 618 variants, and it's relatively cheap, and it's really easy to recreate. As the research that is shown by Hoti and Tapiador. So this is the most uncomfortable evidence the dual use in inside the defense itself. Within the same research that Lee and Istom have made, that is built to detect malicious code, they explored using the model to generate malware variants, raising the dual use question directly, which is my favorite paper because it relates directly to what I'm trying to prove. Is things that are built, or basically LLMs are being built, the things that are being built or researched using defense is also proved the capability to attack. And the barrier is falling as models become more freely available, as the cost of being misused drops. Many standard mitigation loses their force against one model rated as a open distribution, as you can see on the research by De Gregorio. And the core finding is this that really wanted to emphasize is across the defensive studies, the field confidence is running well ahead of its evidence that is supposed to support. And to be clear, I'm not saying that the research is dishonest or the capabilities are fake. They are in fact real. The problem is with methodology, and it really becomes visible when you read the studies all together, which is exactly what we just did. Three weaknesses keep recurring. One, it's a very narrow data set, 133 samples, 200 apps, a single campaign, and the biggest study, which also happens to be only Java only. So nothing is shown to be generalized. Two is really there is no shared benchmark. When you look at a 97% in one paper and a 77% in another, those are not even measuring the same thing, right? There's no honest yardstick, and it's really a gap that one of the researchers called out, many researchers call out to draw the attention to this directly. And three, the one that ties this all together, the models are the weakest exactly where the task that we need the most, which is reasoning, right? 0 out of 7 against real obfuscation, 39% on CV association. They feel precisely where the defender would need them the most. And again, what's the verdict? Um, Large language models are a really great addition to the whole reverse engineering toolkit. Used well, they generally turn hours of manual reading into minutes of review, but they are just simply assistants. They are not replacements for anything. I know the industry is trying to push everything to agentic AI, but it's not really the case here. Their outputs needs checking. We need to understand their limits. We need to have every deployment, or basically every deployment that we make needs to assume an adversary that holds the same dual edge blade. And really, right now, the three suggestions I have after the whole research is really building a shared benchmark, keeping the human in the loop, and really assume a two-side race. Use a common data, common metric, many families and languages so that progress can be properly measured, and let the model propose and flag its uncertainty. Let the analyst verify and assist them to show that where to look, and really defend on the assumption that attackers have the same tool. Look at the risk, reach firmware at open weight models. And let me leave you with one single line that holds everything this talk together. The same capability that helps us read malware helps the attackers to hide it. That is the double-edged sword that I've mentioned throughout the presentation. If we treat these models as brilliant, fallible assistants, not autonomous AI, verify them, understand their limits, assume that the other side has them too, then they are a very powerful ally in the fight. That is going to get only harder as time goes. If we treat them as autonomous agents, because a headline number impresses us, we will be caught out of exactly the evidence gap that I've shown you tonight. And with that, I really wanted to thank you so much. It has been a very interesting project, and really I would really want to thank everyone for listening for the whole presentation. I'll be happy to take any questions through email. This is going to be in YouTube, so feel free to drop a comment. These are some of the references I take. Alongside, I have a more comprehensive references in my written report as well. So with that, I would like to close my presentation. Thank you so much.